Now, just I will to this. Yes. Okay. So, quantum sensors are the new sensors which can ultimately provide the limit of any sensitivity of any physical quantity, physical, chemical sensors or biosensors. They will provide you the ultimate possible limit of any sensing. So those will limit, mean that limit, as I said, the Heisenberg limit of sensitivity of the inversely proportional to 1 by n can be achievable by the quantum sensors only. And these are for using the main three principle of the quantum mechanics. First was the superpositions of the quantum states, which we all know that the states of two quantity, let's say two degenerate state 0, 1 is there, and the superposition of states can define that psi the superposition state. Then the system should be the combinations of these two states where the alpha and beta coefficients of 0 state and the 1 state respectively. And so the second is the enhancements of the states. So that each of the states of the same quantity of the quantum states are similar types of constant state are in a inseparable of combined states, and so you cannot modification in the one state can impact the other state too. So that is the quantum enhancements. So this will allow us to collectively measurement and reduce the uncertainty in the uncertainty in the measurement below the classical limits of any sensors. And the third, the next principle is the squeezing. So squeezing is the mainly nothing. It is nothing but the quantum uncertainty principle, and uncertainty of to conjugate the quantum parameter. Let's simply the positions and the momentum. For example, if the uncertainty in the position measurement is delta x and the momentum measurements is delta p, then we can note that the product of these two uncertainties should be greater than the h cut by 2, where h is the Planck constant and h cut is the h by 2 pi. And here, how accurately we can measure one quantity? We can say that if we want to measure the delta x accurately, then we don't able to measure the delta p accurately. But as per our requirement of the choice, we can choose which parameter we can want to measure accurately. That we can design our device in that manner, and we can accurately measure the accuracies of those quantities. And that the precisions of the measurement I already discussed earlier too. That the classical system we can reach the standard quantum limit where the parameter which can be accurately measured, that is delta theta is the change in the parameter, the error in the parameter measurement, which is proportional to the 1 over square root of n, and where the Heisenberg limit is the inversely proportional to n. So that accuracy can be measured. So now the important of this if we combine these types of property and how we can accurately measure the quantum the physical parameter of the system. So key quantum sensors are the various, we can say. For example, I can say that all the SI unit parameter which we are measured nowadays by classically, which is standardized, it should be measured per accuracy. Accuracy need to be at least 10 to the power minus 8 order, or the better standard limit need to be 10 to the minus 8 or better. That means we can reach 10 to the minus 9 or 10 to the minus 10 level of accuracy in the measurement. That can be doable by each of the this quantum parameter, and that is needed for the future communications for or the any standard measurement of this this quantity. Like simple example, if I again the time can be accurately measured, can be measured by hyperprime splitting constant. That could be useful for the precision measurement of the time. If the measurement of the ampere, which means not only ampere, I measure the all electrical the parameter are like the current, voltage, resistance, capacitance, all could be precisely can be measured. Other the Avogadro number that can need to be measured high precisely. Planck constant means molecular measurement that could be affect the Avogadro measurement, and the measurement of the mass, that kg or the you can gram, whatever you want to say in the unit, that could be precisely measured based on the Planck constant, and the other parameter like the Boltzmann constant will affect the temperature measurement, and the speed means distance measurement can be accurately measured based on the light velocity. So each the quantum parameter, the standard can be helped to define the each of the SI unit parameter which can be precisely can be measured by the quantum sensor or quantitatively. So all cannot be discussed in this class, but as an expert of one of the topics, so I'll explain in details of the current voltage, the parameter or our current voltage parameter. Those can be accurately measured. How the quantum sensing can be helpful to measure accurately current voltage and those parameters. So those the sensors is in the commonly known as a quantum electrical metrology. So quantum electrical metrology is mainly controlled by the quantum metrological triangle. Quantum metrological triangle is a triangle where three major or important quantum phenomena is used to define all the parameter of our electrical system. So the U is the Josephson's of the constant is based on the Josephson voltage, so that is based on the superconducting or the Josephson junctions, and that could be useful all for the definitions of our the basic measurements parameter. Other is the single electron transport device, or you can say single electron transistor. Specifically, you can say other device also there. So a single electron transport devices. Another phenomena is the quantum Hall effect. We all know the Hall effect, which is the linear, the Hall effect resistance linearly depend on the voltage, but the quantum Hall effect is not the linearly depend. So it's depend on the quantized manner, and that could be useful for the detections of or the precise measurement of our current voltage characteristics, and modifications with this phenomena can give the measurement quantized high precision charge measurement and the capacity measurement too. So if just each of this quantity, we can define how this parameter can define the current, voltage, resistance, and the capacitance measurement. I'll discuss in detail. So first parameter, we can see the Josephson junction. So Josephson junction, and basically it's a you can see that just basic example. It's a two superconductor is separated or sandwiched by insulator, means one insulator is sandwiched by the two superconducting states, and this system give the current when the voltage around this junction can be defined as that NF divided by 2E over H, where N is the steps of the the voltage. We will get the step like voltage steps. F is the frequency. The AC signal will apply along this the junction. That is the frequency of this voltage. And where 2E by H is called the Josephson constant, which is a fundamental constant which cannot be changed, which is defined by the Cooper pair charge divided by the Planck constant. So this is a new fundamental constant. We know the H, the Planck constant is a fundamental constant. By in the Josephson junctions, another fundamental constant is the Cooper pair charge divided by the Planck constant voltage. That is called the Josephson constant. So this can be useful for the voltage, the precision measurement of the voltage. So if you see some of the Josephson junction effect, we can see the one of the DC like structure without AC signal. If we see, we can get the voltage current characteristics in the junction should be something like this. And if we have any AC signal, generally we use the microwave of electrical signal for this, and then we can see the step like voltage change. So positive, negative, both sides, we can see the step like voltage change. And if we have the these types of step will be happen when the capacitance value of this junction is small. If the capacitance value is little large, and then we can see the steps is like this step like this, and this will help you in the measurement of the accurate measurement of the voltage. So we can see the step like data, and each steps will define and frequency you have. This the microwave frequency can define your the measurement accuracy of your the voltage signal. And nowadays, the more complex device is designed, and one of the device I have just typically shown here, where multiple Josephson junctions are used, and then your this output can be modified for all this junction, and where we can see the additional the accuracy can be get for the multiplication factor of 2 to the power I, where your I is the number, the n. If the n is a number, then the I can vary from 0 to n minus 1 step. So, and where K1, Ki is another factor which could be 1 or 0, that depend on the which segment of this junction we are used, and which is biased or non-biased. If biased, then we can get 1, and non-biased we can. So this will give you the more accurate measurement of the voltage. So this is one of the quantum metrological parameter which can be more accurately measured by the quantum. It's a quantum sensor, and it will give the voltage measurement accuracy beyond 10 to the power minus 8 limit. Next measurement is the resistance measurement. So how accurately we can measure the resistance? Each measurement, we say the one measurement, we said 1 ohm. Is it 1 ohm? And how the accurate its measurement? This 1.00000 more than standard measurement. It should be accuracy should be 10 to the power minus 8 level. Minimum should be 10 to the minus 8 accuracy to standardize the resistance. So that level of accuracy can be provided by the quantum sensor. So in that case, the quantum sensors we are using, the principle we use is the quantum Hall effect. Quantum Hall effect, if you see in normal case, the Hall effect is the resistance and the magnetic field. You can see this could be the linear effect, and here you can see that for the example just I'm giving, that you can see the resistance is varying step-like manner. Each of this resistance you are seeing that step-like manner, or that step is depending on some factor is nu. It could be we define it's 1, 2, 3, etc. It's a if it's a integer quantum Hall effect, this nu should be 1, 2, 3, etc. Or it could be should be some fraction, and then we call it the fractional quantum Hall effect. And the parameter, resisted parameter or resistivity, you can also that the resistance is along the xy plane in the quantum Hall effect. If we know the basic Hall effect, that the resistance now can be the normal cases. This should be linear. The Hall voltage divided by the current, ratio should be linear. But in this the specific case, it should be the h over e square, or in the factor of nu. So mu is the parameter which will define is the 1 for 1, 2, 3 for the intrinsic Hall effect, and for the other effect like it could also be fractional. Fractional value is various depending on the various combinations of the quantized magnetic field and the electron. So nu could be 1/3, 2/5, 3/7, etc. And simply, I just want to give it the what is happening in the quantum Hall system. You have the few number of electron you consider. You have a two-dimensional system where your z direction is confined. That the z direction is confined means your quantum state along the z direction is very high value, is discrete states. Let's simplification. If I say your energy of this energy separation of this quantum states could be few millielectronvolt, let's 10-20 millielectronvolt. And now each of this electron, when you apply the magnetic field, can move in a cyclotronic motion, and they can give a quantized states of the electron and magnetic field, and they will generate a different equi-energy separate states, and those states we call the Landau states. And those Landau states are the smaller value, very smaller value than the electronic states. What I say, the 20-30 millielectronvolt is to be smaller, maybe the less than millielectronvolt. And if you reduce the temperature of the system, then electron can those number of electron can sit in the lower this Landau states, and you can get the resistance on the system. And then you increase the temperature, you increase the temperature, or you simply change the magnetic field, lowering the magnetic field. Some modification will change, and occupancy of the states will modify in a discrete manner, and you can see that this jump in the resistance in a discrete manner of nu will happen. And in the fractional states, that is a complex system. I will not discuss here. But the integer quantum Hall effect is a more important, good enough to deal with the high precision measurement of the resistance. So some of this principle we can use that the voltage, we know that the voltage U, this is can be the Josephson function voltage in the modification state. So it should be coupled with resistance and current. Current can be measured by the single electron transistor. And now from these two relations, the Josephson voltage and the current, the single electron transistor can define this current with precision measurement. They can combinedly give your the precise measurement of R by the R could be U by I. That way we can get. So it is not simple device. It need to couple a single electron transistor, one superconducting Josephson junction, and then which resistance should be measured, that resistance. So one of the complex design is given here, where that the resistance which we want to measure or standardize, that should be very low temperature, let's say the cryogenic level of helium cooling temperature and 4 Kelvin temperature, that should be coupled with a single electron transistor, and then you have a superconducting states Hall system. All should be the coupled to each other and to get a relations of U equal to R dot I, and then we can define this. So then the basic relation can be modified, that the voltage should equal to resistance into current should be modified to the discretize the voltage of the Josephson junction, and RH the Hall voltage, and the I and G is the some gain factor depending on the system used for the capacitance measurement. So it's a gain factor. All the relation is actually Uj equal to RH with the Hall resistance and into current. So if combine this is the Hall resistance, the Josephson junction voltage, RH the Hall resistance, you have the Hall bar, and if you have the current of ACT, then this relation should be modified like this, where Uj, you know, the Nj of J by Kj, and the RH is Rk by J, and G is a factor, and you can find current should be Qx into FACT, where this factor coming from the voltage, the superconductive junction, and this factor is coming from the ACT, where ACT is depend of the F is ACT is the frequency applied in the single electron transistor, and the current is the measured current. The I here I is the index of the quantum Hall states, that so where we are measuring that the index which states we see, that could be the index of the system, and you can modify this with the simply to get the Rk value. The Rk, Kj, and Qx it can be find as the Nji over G into Fj by Fac. So from that we can accurately measure the Rj in a discretized manner, and we can get more accurate measurement of the resistance. And the combinations of this with the capacitance is Q voltage capacitance and the charge relations. We can also convert same system to the capacitance, accurate measurement of capacitance. Another important parameter of the current voltage system is the current measurement, that is ampere. And ampere are in generally we know that how the standard by ampere is measured based on the two standard or current wire, which is used for the electrical wire is basically, as I recall, some combinations of alloy is used, and there if some magnetic field current flow between this with both the wire, and they generate magnetic field, and the force between these two wire can be used for the measurement of the ampere. This is the standard classical technique or used in the SI unit. But if you want to accurately measure this current, we need to use the more accurate system, that is the quantum system. And this system we generally call as a quantum current metrology or quantum or single electron current metrology. Single electron current metrology is used by device, two types of device. One is the single electron pump, another device is single electron transducers is there, so or transtrial is there. So single electron on transtrial or single electron pump can be useful for the accurate measurement of the current, and that the current can be measured by this relation, where NEF N is the number of electron per cycle it's passing through the junctions of the single electron transistor, is the current level, and F is the frequency applied in the circuit. So this system will help you to detect the better accurate measurement of the current. And one of the example I just giving you here the real device, where use a single electron transistor, and they use multiple gate system, and the electron transfer from the it's a transistor where ACT is a single electron transistor, where source you have the quantum dot and you have the drain level and you have the gate, and this electron can go from the source side to the quantum dot and quantum dot to the drain side, and the barrier of this two junction can be modified by this gate, and you can apply the AC signal between one of the circuit, maybe source to the gate voltage or the gate to the drain, and you can tune the barrier in between the transport from source to drain via the dot. So potential diagram, you can see that if this is your the quantum dot, and the in between source drain you have two barrier, and electron can be trapped in between this. And by applying the signal voltage, you can modify this barrier height, means amplitude of AC signal can modify the barrier height. Once situation, you reduce this barrier height, so electron can enter in the quantum dot, and you modify the amplitude that the barrier is high, then the system should be electron should be confined within the quantum dot. And if you reduce in the opposite cycle, when you reduce the barrier height of this junction, and the electron can move out from this. So this is the reverse can be done by changing the signal in oppositely, and electron transfer from the source to drain via the quantum dot can happen, and by the controlling the AC amplitude of the barrier by applying AC signal or AC voltage, we can transfer electron one by one. And the schematic circuit means circuit diagram of the system should be something like this, where you have a voltage and you have AC, you have the pump, and you have pump current, and you have the current measurement you want to do through ammeter, that is the AC ammeter you can consider, and through this system you can detect this adjustment can be done, and you can get the current measurement accurately. So some data of this device with the voltage, this gate voltage is one of the gate voltage. You can apply it with the different voltage. You can see one of the data. Just see, you can see the step. So you can see N is the number of electron passing through this junction per unit time. That you can see that this is one. Once applied voltage, next different voltage, you can see that each times you can see the measurement is perfectly one electron. So one electron accurately can be detected by this single electron pump, and the frequency and can be measured by applying frequency. You can tune the speed of this measurement and the accuracy of the system. Nowadays, the earlier megahertz frequency was used, and nowadays also some device gigahertz the signal frequency are used to for this measurement of this current measurement. So that's I just say that three important factors is there to define the electrical signal. One is the quantum Hall effect, with another one the superconductive Josephson junction. Third one is the single electron transistor. So single electron transistor is the one of the component for each of these measurements. Single electron transistors can be independently measured the current, and if it coupled the Josephson junction and the quantum Hall system, and they can measure the other things. So ACT is the main component for each of this the standardizations of the electrical component. So we have to know what is single electron transistor, and how they can be improved, and what is the standard of this system. So if we schematically design a single electron transistor, we can say that you have a source drain, and you have a quantum dot, and this quantum dot could be separated by two junctions, to barrier junction. This junction are called the tunnel junction. Tunnel junction means it's have the capacitance and resistance, both value. That means it can transfer electron through this. It not stop the electron. It have some finite resistance value. It should have the finite capacitance value. It's a combined system, and it could be controlled by the gate, and this gate has only the capacitance. It's an infinite resistance, but have a capacitance value. It's the finite capacitance value, but infinite resistance value. So we have two tunnel capacitor and one normal capacitor, which should be used to control the potential of this quantum. So in general, you can design the system in several ways. It could be this quantum dot could be a metal, and you can design. You can place some insulator in between with few nanometer or thick insulator layer, and then you can have the system. Or you can have a semiconductor quantum dot, and that could be separated by some insulating gap, and that could be some insulating. It should not to be a pure perfect insulator. You don't need. You have some the potential. There should have some potential barrier need to be there that we can control the system. So if we have the equivalent junction circuit of this, we can draw something like this. You have the source, you have drain, and in between the quantum dot, you have two tunnel capacitor, and this gate is coupled to the normal capacitor, and the voltage should be applied to control the parameter of this quantum. So if we want to draw the potential diagram of this system, it could be look like something like this. You have source, and you have a quantum dot and drain, and in between source drain and quantum dot, source and quantum dot to drain, you have a barrier. It's a tunnel barrier. Tunnel barrier means it should have the property that the particle can tunnel from the source to drain, or the source to quantum dot, or quantum dot to drain, or the vice versa in the other junction. So that means your barrier should not be so high, infinite, or the thickness of the barrier should not be so high. So it's combined that you have the tunneling probability that the particle, here we consider charged particle, let's electron can move through the barrier, or that is possible. That is the tunnel barrier. So you have to tunnel barrier, and the gate should be applied to control this barrier height. That is the important. So to operate the single electron on this system, one is the major phenomena is the Coulomb blockade effect. So what is Coulomb blockade effect? Or simply I want to say if you have some electron in the quantum dot, let's assume one electron is there, then another electron, if you want to enter in the quantum dot, there is a Coulomb repulsion. So incoming electron and the another electron sitting in the quantum dot, they will repel each other by the Coulomb repulsive force, and that is called this force. If we measure in terms of energy, we call that the charging energy. So if you have some junction and you have the capacitance of each of this, then this charging energy, one energy required to enter one electron into the system, it's called the charging energy. That charging energy is nothing but E square. E square is the electronic charge, or E square by 2C sum sum. C sum sum is the capacitance, all sum of this C1, C2, and CD, sum of these three capacitance, that will give you the charging energy. So what is the criteria to get such device to operate? That charging energy, this charging energy must be higher than your thermal energy. Thermal energy in room temperature is kVT. If we say the room temperature is 25.8 millielectrovolt, that is your energy. So to get this device to operate, this charging energy must be higher than this value. Otherwise, we cannot see this phenomena. Thermal energy will thermionic emission, or the thermonic current will overflow, and we cannot see this ACT current. Another phenomena is required to get this is the tunnel junction that will appear. The resistance of the junction should be, it is coming from the uncertainty principle of energy and time. We can use this principle and derive the equations where resistance is required, resistance, and or we call the quantum resistance, which is h by 4 pi e square. That the resistance of the junction must be higher than the quantum resistance, which is h bar 4 pi h over 4 pi e square, which the value is 25.8 kilo ohm. So this amount, to be a tunnel junction, the resistance of this junction should be higher than this one to see the Coulomb charging effect. Otherwise, the system should be resonance tunneling, and the Coulomb blockade, this repulsive phenomena cannot be detected. So, what should be a system? What the characteristics we'll observe if we have the single electron transistor? If single electron transistor have a quantum dot which have discrete energy level. Discrete energy, in case of the metal quantum dot, we cannot distinguish the this energy level, but it's a semiconductor or quantum dot, then we have the discrete energy. So if electron enter from one level to the other, it can enter and go out, we can see one current peak. If we apply gate voltage and we align this energy level with the source and the drain reservoir, this is source, this is drain reservoir, then electron can enter here and go out from the system, and we can see one current peak. For next level, the peak, the electron can, we know that each of this level can accommodate 2 electrons by the Pauli exclusion principle. One is the electron spin up and another spin down. So if we assume first one is the spin up, then the second electron will come as a spin down state, but it can accommodate in the same energy. But if this electron even can enter in the same electronic level, but they are separated by imaginary energy, that is the repulsions of this electron to the next electron which are entering. That is called charging energy, and that need to be overcome by applying the gate voltage. So you can see a virtual states of the charge state, which is here, and you can get the another electronic peak. So for the first electronic level, you can get 2 current peak, single electron current peak, which is separated by the charging energy. For next level of entry, that is the next level here, so it is separated by, let's assume, by delta E. So to give this current, we have to enter the separation of this energy, that delta U need to provide, and then you have to add another, the charging energy must be there. So for the third electron entry, you need to provide ECH plus delta E for the semiconductor quantum dot. If it's a metal quantum dot, this delta is negligible. You can see each is ECH. So this phenomena generally we call is the quantum Coulomb blockade phenomenon, where this state should be in general be separated by ECH plus delta E. Again, it should be ECH and then ECH plus delta E. So this is the quantum Coulomb blockade phenomena we will see in the thing. So this is the standard. We can design the semiconductor quantum dot based or metallic based quantum dots. We can define another types of the ACT. We can use even a single atom. Single atom can be used as a ACT also. Where how we can place? If we have a source and drain, in between, if we place a single atom, and it could be impurity atom, it could be donor. Let's simply a phosphorus in silicon. If we place, then we have a potential like this one, and this potential can be controlled by the gate. And if we apply this gate voltage, some alignment of this quantum state will happen to source and drain, and current electron can pass through the quantum dot, means the impurity atom, and you can get ACT like current peak. After that, over the barrier current will flow, this we can see the ACT current. This is the new types of the ACT, which few group in the world are working, including me. We are focusing that the impurity can be used for the single electron transistor, and then we can make the simplest or the smallest quantity of the transistor, which is the single electron transistor that could be made. So, this device is another type of ACT. So we are using this types of ACT for different types of detection. So what types of detection can be used? This ACT can be used as itself is single electron transistor, that is single electron emitter we can use, and various applications. As per I said, thus any single electron transistor can do this. Single atom single electron transistor can also do the same phenomena. So it can use the single electron quantum metrology, electron metrology, other phenomena it can be. It can also be used single photon detection. It can be used, the most important thing is the quantum computing, and that could be various types of quantum computing are there. Spin-based also two types, is the nuclear spin-based or also the electron spin-based. Both can be done by this single atom transistor, and also charge-based quantum computing can also be possible by this single atom transistor can be used for the charge-based quantum. So our group are focusing various factors, or one is the single electron transistor we want to make. We want to use the single electron single photon detector by these types of system. We can also are in plan to do the single electron quantum metrology, and also our group is focusing on the charge quantum computing using the single atom devices. So we are focusing for the charge-based quantum device, because quantum bit, because of we want to work the high temperature quantum bit or the quantum computer development. So that is not feasible for the spin-based system, because Zeeman splitting is there, and that cannot be separated by thermal fluctuations, cannot be separated. So the spin-based qubit can be operate only low temperature, but charge-based qubit can work at high temperature, and our group also focusing on this. So one of the examples, just want to give you our recent work, is the single photon detector. So single photon detector, we want to use a silicon to detect the single the SWIR, means short infrared light detection. So we designed a system. Short infrared light means around 1500 range, 1500, 1700 nanometer, which cannot be detected by silicon, because it's the opaque range of the silicon. Above 1100, silicon is transparent. So we cannot detect any signal, any wavelength, photon wavelength above 1100. But we designed a system using single electron transistor that can detect a single photon, even 1700 nanometer, and that can be detected in a single electron or single photon level. So one device we use as a single electron transistor we make using the combine of the dopant. It's a heavy doping system, and it's a two types of doping is there to adjust the energy level of the band of the phosphorus, means conduction band, and the valence band modification can be controlled, and that's why we do code of system we design, and device is controlled by the backgate to operate for the photon detection. And the device we design is you can see the channel region, the source and drain, and the channel region is very less than 100 nanometer, and thickness of this device only the width of this device very few nanometer, around 10 nanometer, and also the device thickness we also measure is below 10 nanometer, both ways that is the system. And we have this device, and we measure the characteristics of the device, the current voltage of this device by using the backgate voltage, and we can see the several ACT current. We can identify each of this ACT current peak due to the single of phosphorus atom, and we identify around 5 single phosphorus atoms give these types of the ACT current peaks. And this the current voltage measurement in the drain voltage and the backgate voltage plane give the stability diagram, where the current is measured in the color bar, and this x-axis is VD and y-axis is the backgate voltage. we can see the phenomena of Coulomb blockades. You can see that these are the no current region where we can the current is we are not getting any. These are the blockade region. This is the high current region. This is the current peak we are getting. Even in this stable, we get the stability diagram of the Coulomb blockade phenomena, and the characteristics of this device can be controlled by their complex states. I don't want to discuss here. But whenever we apply the bias voltage here, we apply any photon, here we use a 1780 nanometer photon, and we see a huge step in the voltage. You can see the current peak is -3 volt, and the voltage now shift to -0.5 volt. So around 2.5 volt shift is there. This small shift, this huge shift happened due to the detection of large number of photons in the system. So even you can give a single photon fall on the system, you can see a shift, and that shift can be useful. Shift can be used as a sensing for the photon. So even single electron absorb here, and that could give a shift. So here we have the area, a large area of source drain, open source drain. That's why we absorb multiple photons, and we can see a huge shift, and we can get a shift. So this is one type of sensing we did. Another important sensing we did with the random telegraph signal. We measured the random telegraph signal with the photon with time, and we can see the jumping of the current level to the high to low and high to low. So low level of photon injections, we can see the two-level system. If we have more number of photon injection, multi-level system, multi-level incorporated during the photon current detection. So this type of system can be get by the trapping and detrapping of electron induced by the photon. And if there is a the ACT current is there, if the photon is detrapped from the system, you can see a shift in the current, and that's why you can get the shift in the current voltage as well as the current level. We can see in the transfer in the random telegraph signal data, and those can be detected, and we can modify the silicon by using the heavy doping. We change the band to band transition, and so we modify the absorption limit of the silicon by more than 1100 nanometer, and that is also detected by the absorption coefficients measured by the electrospectrometer, and we can make the silicon as the SWIR detection, and as per our data, we can also do the MWR detection by this system. And if we see the sensitivity measurement of this system in terms of noise equivalent power, we measure the sensitivity of this system is of the order of 10 to the power -19 per watt per hertz inverse. This is almost one of the highest sensitive of measurement of the photons in the system. If you compare with the other system which are exist in the few literature, that the normal FET, we don't get any P level of detection. Some antenna-based quantum dot system give the sensitivity is of the order of 10 to the -30, where we reach 10 to the -19. The silicon MOS based Schottky diode based detection reach the this is the classical detector which reach the sensitivity of 10 to the -9 order, or where some quantum dot nanowire based ACT system also some level they reach around 10 to the -12 level. Other detector also reach 10 to the -16. So we reach 10 to the -19 level. Our measurements are done at 5.5 Kelvin temperature, and some device is measured by gallium arsenide ACT system at low temperature, which is around millikelvin temperature, which have the sensitivity is of the order of 10 to the power -21 also. That Professor Komiya group from Japan did that one 10 to the minus 21. That is also very low temperature, but our measurement is quite relatively high temperature, or 5.5 Kelvin, but this is a still low temperature system. So we can do, we have to improve this device if we want to use for the day-to-day application. So the system is needed for room temperature, or the high temperature or operations is needed. So we want to use this system for high temperature operations. How we can do this system can be operate for high temperature. We are working on several important aspects. So those will have various advantage. We can say that all the system can be measured at room temperature, means we can day-to-day application, we can do everything. So that's why our group are focusing on high temperature quantum operation. So this dopamine system can be doable for the high temperature operation, but we have to deal with several important factors. One factor is the charging energy. As I say, that charging energy should be very, very high, greater than the thermal energy of room temperature. As you know, the thermal energy of the room temperature is around 26 millielectrovolt. So to operate the device at room temperature, this should be charging energy at least should be higher than 8 times higher than the thermal energy. So it should be around 200 to 300 millielectrovolt is needed to operate the device to overcome the thermal noise or the other noise. You need to make the charging energy in that level greater than 200 millielectrovolt is highly needed to operate the ACT at high temperature. Another important factor, if your system is with quantum dot-based system, you have the energy separation. That energy separations of the two consecutive states, that should also be higher than, must be higher than, and this cavity room temperature. So if we do this, then only this device can be useful for the quantum sensing, various quantum sensing as I described, at room temperature or near room temperature, or that could be our day-to-day we can able to apply this device. But doing this device is very, very difficult. As you say, the normal phosphorus in silicon have an energy of only 45 millielectrovolt, and that 45 millielectrovolt is not more than 20, even not twice than the room temperature thermal energy. This device generally operates around 20 Kelvin temperature. So we cannot go higher than this level of temperature to operate the device. So we want to operate, if you want to operate the device in high temperature, we need to do the confinement of this. Three different we can do the confinement. One is the dopant can be confined. Another, we're trying to do the multi-donor or molecule system, and the another is a deep dopant. So we tried one by one system, and recently we have fabricated one device where we use two types of confinement. One is the quantum confinement, another is the dielectric confinement. And in general, dielectric quantum confinement is more stronger than the quantum confinement, and we did both, and the device can operate around more than around 200 Kelvin temperature, which the single atom based phosphorus dopant based device, which can work at lower temperature. Now we can operate a device at room temperature, and this is suitable to do the further improvement for the high temperature operation. And these are the other characteristics of this device. I will not go further. And we also do the multi-donor device system, and we reach a device which can also operate at room temperature. This device can operate at room temperature. We did the clustering of the phosphorus donor. Here we did 3 donor cluster, and to make an energy level of around 180 millielectrovolt, and this device work at room temperature. You can see the ACT current with sustained state at room temperature. And we also did another method where we use the confinement and not confinement. There is a limitation of technological development, and the clustering also have some certainty in the fabrication of the device. So we are focusing on the deep dopant based device, where deep dopant is the the device which have itself at the higher energy, a higher energy, which is around 200 or more, and the separation of the states in the dopant is the higher. And we choose a nitrogen-based system is our own proposal, and we saw that this device could be suitable for room temperature or operations, and that could be also, we did theoretical calculations, so this system can be useful for room temperature quantum bit operation and single electron transistor, etc. So we are now fabricating this device for such applications also, and so this type of device you can see can be used for the sensing technology. And the other sensing technology, if you say the quantum biosensors, I just give two examples. One is the tunnel FET-based device, and another is a single electron transistor-based device, which are very even it can able to detect the single molecule, and if room temperature acidity with high peak to valley ratio can be developed and can change the scenario of the quantum biosensing. Those are under work, and we are also working in that direction. So some comparison table, if we discuss in the classical to the quantum sensor, you can see the quantum classical sensor can really on the macroscopic physical property like piezoelectricity, thermoelectricity, photodiode, etc. But classical sensor, quantum sensor operate in the superpositions of the quantum states, intelligent states, and uncertainty principle. And sensitivity, we already discussed in the classical sensitivity is the SQL limit, or the quantum sensor is the HL limit. Dynamic range is here wide, but here the quantum level is the very narrow range we can detect, and we can precisely also detect this. So accuracy wise, this even one of the example, this accuracy is very high in quantum level. So optical lattice clock, if we design the accuracy, the fractional uncertainties of the order 10 to the power minus 5, the 18 in the auto level is the accuracy. So the advantage in the quantum sensor have the huge advantages, but you have the limitations also. Quantum sensor as a fabrication wise, it's a very complex designed, and you need a very sophisticated laboratory is needed, and but you can make the accurate sensor, and our life should be easy, I can say. But for that, we have to improve the technology up to room temperature for day-to-day operations if we want. So these are the future direction people are working to improve the scalability of the sensor, coupling with the AI and machine learning. There and the scalable quantum sensors are in the plan. The wearable sensor, if you couple to the quantum sensor, those would improve the system. So these are the basics of the quantum sensors and the classical sensors. So we have established the quantum device fabrication laboratory at IIT Roorkee in the Department of Physics. I am leading the laboratory, and we help with some of our results, which are help from our student. Our collaborators are there internationally and nationally. They are helping. So for some funding we are getting from several national international agencies. And thank you. So if you have queries, let me.
Thank you, Dr. Arup Samanta, for your wonderful lecture covering all like aspects from classical to quantum sensing and the application part. So we have some queries in the chat box. If possible, maybe you can scroll down, or I should read it.
Yes. PowerPoint sharing, then I can see chat box. Yeah, I'm just got the chat box. So
Yes.
the first questions I am getting is that okay, this is different. So I am just going to the related to part. Can we detect frequency just like spectrum sensing in uh, conductive radio using quantum technology? So you can see that you can apply the which types of frequency you want to detect. So in the quantum metrological triangle, you can see one parameter is the frequency. So if you design the system and other parameter like the current I equal to N and E into F is there, so you operate during this. So if you apply that N is fixed, I is fixed, and F is there, and if you have the fixed frequency, now if we apply the external frequency on top of that, like the you can apply the photon onto the system, and if in the range of detection of that, then you can able to detect that. So that modification can be detected from this in the frequency level. So which types of frequency you want to talk, that is also important. So next level is
there any possible way to reduce quantum noise in detecting weak biological signals?
yes, quantum noise you can be reduced. You can see how you can reduce the noise. As I said, all of the source you have the two level system. As I said, that you have to consecutive. Let's to reduce the noise. I said that if you want to operate a device at room temperature, all noise will be increased. Short noise, the resistive noise, every noise will increase. How to reduce this? That's why I choose a parameter, as I said, to for quantum device, which will sustain only if the thermal energy, the energy is that the thermal energy, then the system of the quantum should be at least 8 times higher than the thermal noise, means thermal energy. So if I include all noise in the thermal energy, that is room temperature is 25, around 25 to 26 if millielectrovole, the quantum system should have 8 to 10 times higher than this energy level. So the charging energy should be higher than that this 25 millielectrovole. So minimum should be 200 millielectrovole. Another noise is coming is the separations of these two states. So the quantum dot itself should be separated. The internal energy, inter-electronic states of the quantum dot must be separated more than this thermal energy. Means at least 6 to 8 times than the thermal energy. Then only we can reduce this. So we have to operate this device high temperature or even any low temperature if you want to do thermal energy there. Let's you have 1 millielectrovole thermal energy. So even in that case, to operate the quantum device, your system energy should be 10 times higher than the thermal energy. So separation should be around 8 to 10 millielectrovole. Then you can avoid this noise. So we are designing the system based on our practical application point of view, how we can ignore all this noise. And this is one professor already calculated that this should be the order of magnitude to avoid this all types of noise.
Question is how do physical sensor maintain stability in extreme conditions like temperature, humidity, vibration?
So if you want to do quantum sensor, at present, all the quantum sensor are low temperature. Mostly in millikelvin temperature, only few group are trying to do in the high temperature, including us. So for ACT-based system, few people, as I recall, from Japan and South Korea, and also from France, very few are reach room temperature operation by single electron transistor. So other application they did not. And quantum dot means impurity-based system. We are the only group in the world, including our collaborator in Japan. We did the room temperature operation, even high temperature around 200 Kelvin to more than 150, 200 Kelvin operation temperature. The most of the maybe the photonic sensors, those are photon-based system can work maybe in photon waveguide-based system may work in the high temperature. But if you want to single atom, even the coal atom or trap ion system, those are should be trapped in the low temperature. It's also in the millikelvin temperature. So only the condition if you reach that your separation of the energy level of the quantum dot or atom or impurity anyone should be this higher order than the thermal energy. Which temperature you will choose to operate a device minimum 10 times higher, 8 to 10 times higher should be required. 10 is better or at least 8 is required. We observe experimentally these things.
So maybe last question, this TEFT sensors are highly effective in detecting very low concentrations. How can they be used for differentiate the noise from the actual signal?
So I cannot catch the questions.
This is the TFET sensors.
TFET.
Yeah.
Okay, TFET, tunnel effect sensor.
Yeah. So they are highly effective in detecting very low concentration. How
Yes.
can they be used to differentiate the noise from the actual signal?
Because tunnel effect is a tunneling phenomena, you can get similar to the peak of the ACT. So some peak is there. So if any changes happen in surrounding phenomena, means your dielectric constant is changed. So ultimately, it affects the capacitance of the system. So if any capacitance is changed, you have the tunneling phenomena electron. So close to a tunnel effect is close to the single electron on of current level, close to not up to the level, but I can say the little away, but along that direction than the classical sensor. So any change in the capacitance happen, that should sense by the sensor. So if we have one molecule, some shift will have two molecules, another shift will be 3 molecules, shift should be higher. So this shift can be quantitatively measured or to detect the sensing.
So maybe this last question, what is the best book on basic quantum sensing?
Means basic means which types of?
They are asking this to basic quantum sensing communication.
Means you have everything can be converted to quantum. So means as a if any this every system is quantum, but we able to means each state is discrete, but we able to detect or not. That will define it's a classical or the quantum. So let's simply consider your bulk system, metal or the semiconductor with size of 1 centimeter. You say the quantum states present in the conduction band. So that separation between the states is of the order of 10 to the power minus 15 electrovolt. Separation of the states. This is also discrete, but separation is only 10 to the power minus 15 electrovolt, where thermal energy is 10 to the power or means millielectrovolt. So if you compare the separate thermal energy, how much the higher than the separation of state is 10 to the power 12 times higher. So if we have any electron there, you have the staircase of separation, and the electron can go to the sky, even the faraway star. So you cannot see the states. So that's why you call it a classical. But if your separation of the states become 100 millielectrovolt and room temperature is 25 millielectrovolt, now its separation is the 4 times higher than the thermal energy. So now you can see the discreteness of the phenomena. So you can able to detect it. That's why now it's become quantum. Both is there, but the separation of the states you can able to detect it's overcoming the thermal energy or not. That will distinguish the quantum measurement. Measurement wise, that is you can able to measure or not. But states is always there. It's all are quantum states.
So thank you, sir, for your lecture and answering the queries. So if there are any further queries, maybe I will encourage participants, they can write an email to get the answer. So on behalf of the organizing committee and this E and ICT Academy, so we thank you, Dr. Samta, for your lecture today. And so this way we are come to the end of the third day of this FDP. The lecture files till yesterday already shared with the participants. We will share the today lecture slides shortly. as you know, they're like most of coming days, they are having festival. So they may vary across the different region of India. So I wish everyone is happy Durga Puja and the festival, and we will meet on 3rd October at 3 p.m. Sorry, 2 p.m. So we will keep you posted in the group. So please enjoy the festival, and we will resume our FTP on 3rd October at 2 p.m. Thank you very much, everyone.
Thank you. Thank you very much.
Thank you.